lot of things. TRH and LHRH are examples of some small or large molecule neurotransmitters. Just so you see where it all kind of fits in. So these are small chemicals that are being sent from one neuron to another. So acetylcholine itself, the biosynthesis of that, you've heard about acetylcholine every time you've studied muscle, neuron-muscle junction, that neuromuscular junction, the release of acetylcholine. And so we talked about that during the cardiac lectures with the cardiac muscle. And so anyway, we didn't say what it is, but it's from acetyl-CoA, which was the thing along the way, the 2-carbon plus that coenzyme A arm that's that step before the Krebs cycle of a big enzyme. And so anyway, that's utilized along with choline, which is just sort of kind of like a B vitamin sort of thing bit along the way that gets transported in cells. And those two things get connected or glued together via choline acetylcholinase, choline acetylcholinase chat. Anyway. And then it's transported into vesicles. I can't talk right now. By that. So vesicle-associated transport. So how does stuff get in vesicles? Generally, vesicles are formed via the Golgi. And so stuff is made, stuff meaning proteins, along that endoplasmic reticulum. It bubbles over to the Golgi, which bubbles into these vesicles. Well, what if something is made in the cytoplasm that wasn't a protein that needs to get into a vesicle? There are vesicle-associated transporters for that. And so this is a specific one for acetylcholine. So chat made acetylcholine, and then chat got to its vesicle by that. And then they're there. So you know that neurons have this axonal terminus full of vesicles that is full of neurotransmitter. And so the one you know best is acetylcholine. So that's how it gets made out there in the cytosol and transported into the vesicle, and then it can be released into that synaptic cleft. That's via exocytosis, response to a calcium influx, which was part of that propagated action potential. Opened voltage-gated calcium channels, which instigated this whole release thing, and that's by the snare complex. And I really just, as I was going with all the letters, thought I would keep it up, but I don't know if you studied those, but it's just a way, and it's not something that is important necessarily, it's just the whole, how do you get the vesicle to burp to the outside? And for the most part, plasma membrane with vesicular membrane will naturally attach, but you do have to have proteins that will enable that. So there is a protein complex on the plasma membrane surface, the cytolic surface, the cytosol surface of that plasma membrane. And there are proteins over here on the vesicle that will help dock that vesicle and help release for the exocytosis of that vesicle into the inside. And so it's really the calcium influx that's enabling this docking of the vesicle to the plasma membrane for exocytosis. So it's incredibly cute. You know that it is. It's not accidental. And it's calcium that facilitates the snaps and the vamps coming together and making it all happen. Yeah. With jazz hands. Yes, with a flourish. So anyway, that is a protein-mediated event for exocytosis. And then you have the acetylcholine into the synaptic cleft. So there it is. Here's kind of a picture that should pretty much show the process. The choline is being transported in. Acetylcholine is being connected to choline by chat, inserted into the vesicle. And then at such time that the action potential is propagated to the axon terminus, then that vesicle will burp its interior to the exterior, and you'll have acetylcholine in the synapse. Well, that's only as good as long as it lasts, and it's only as good as the receptors being able to receive it on the postsynaptic membrane. And this could be muscle cell, or it could be, this synapse could be happening in a ganglion, and this could be a postganglionic cell on this side receiving the acetylcholine. So acetylcholine will be out there in the cleft. It has a really short half-life, and then it's degraded very quickly by acetylcholinesterase, which will just cleave it into and render it useless. A lot of that can be recycled back into, those components back into that cell for recycling to make that make more sense. So there you go. That's the whole little process with acetylcholine. Cholinergic fibers are those that are releasing acetylcholine. And so those are somatic motor neurons, everything exiting the CNS. So autonomic nervous system, preganglionic fibers or neurons. The word fiber, neuron, axon, kind of all interchangeable there. Axon would just mean the extension, would not include the cell body, but those are all just kind of exchangeable words. Parasympathetic, post-ganglionic ganglia will release acetylcholine. There's a lot of communication within the central nervous system where neurons are releasing acetylcholine to other neurons. So when in doubt, acetylcholine, I would say. Yes, unless it's sympathetic. And then you're saying norepinephrine. It's pretty clean. And so the thing that's receiving the acetylcholine is a cholinergic receptor. And I put those places in the brain that actually communicate with acetylcholine, but I don't care what they are. So they're just there so that you believe me. But we're interested in the autonomic nervous system, but there are acetylcholine receptors, can be two flavors. Nicotinic was one, muscarinic is the other. And I feel like we talked about this a bit here and there, but so the nicotinic receptor for acetylcholine is going to be skeletal muscle, and then some places in the central nervous system, and then also some autonomic nervous ganglia, because preganglionic nerves are synapsing with and exciting postganglionic nerves. So nicotinic receptors, it's a ligand-gated ion channel. So it's just a central channel. That nicotinic receptor is going to be these transmembrane proteins with a center channel or core that will, when you bind the acetylcholine, will cause an influx of cations, which will then propagate some sort of potential on that receiving membrane, or some sort of activity like muscular contraction for skeletal muscle. Nicotinic receptors receive acetylcholine either at skeletal muscle or at postganglia plasma membranes of the autonomic nervous system. Now that other flavor, muscarinic, is going to be out there on effectors. So smooth muscle and glands, or maybe located within the central nervous system. So muscarinic receptors, the other flavor, acetylcholine receptor, there are subtypes, of course, and they are just distributed to different tissues. So muscarinic 1, acetylcholine receptor. That's what all of those letters mean. Muscarinic subtype 1, acetylcholine receptor, is within the autonomic system ganglia. So all of those times that preganglionic neuron from the parasympathetic division, maybe it's traveling along the vagus, it gets to its ganglion, it's releasing acetylcholine, and that receptor is a subtype 1 muscarinic receptor. So that's what that means. And then for cardiac tissue, there's subtype M2 or subtype 2, smooth muscles and glands, subtype 3. There are 5. The other ones are really going to be within the central nervous system itself. And so what the results of those things are is going to be specific to where it is. So remember that the neurotransmitter is simply the signal. It's it's the receptor and what cell that receptor is sitting on, what subtype it is, that determines what will happen in that postsynaptic cell. And so the muscarinic receptors are, or the nicotinic ones are ion channels. The muscarinic receptors are G protein coupled receptors. So, yeah, a little bit slower maybe than the gated ion channel. The ligand will bind, and this is just completely redundant information. What a G protein receptor is, the ligand is bound by that receptor. G protein is activated, and it activates a series of second messenger systems that will either change cyclic AMP levels, up or down, or calcium levels and protein kinase C activity. And so depending on where they sit, there'll be different kinds of second messenger systems associated with that G protein, which I know just continues to turn you on every time you hear it. But it does make the pharmacology a little tricky, right? When you're talking about these, all this stuff. But the action, when it is a muscarinic subtype 1 receptor sitting in those autonomic ganglia, will be that it utilizes that phosphatidylinositol pathway, that calcium pathway. The receptor sitting on the heart, decreased cyclic AMP. The one sitting on glands and smooth muscle are using that DAG and IP3 thing. So just to show you that there's a different place, a different signaling system depending on where that sits. And that result will either be excitatory or inhibitory, depending on what it is. The other neurotransmitter, so there are two big neurotransmitters to discuss within the autonomic nervous system, acetylcholine, and then the other is norepinephrine. And there are a lot of flavors of receivers there. So first, the norepinephrine, which we discussed a bit in the adrenal gland stuff for endocrine. And that you start out with tyrosine, a series of enzymatic decarboxylations and methylations result in norepinephrine being made. Norepinephrine is really the number one neurotransmitter released. So it was by the sympathetic nervous system fibers. So remember that it's really epinephrine that's more common for adrenal gland. That norepinephrine got pumped back out of the vesicle, methylated, and then pumped back in, so epinephrine was released. When you look at a sympathetic nervous system post-ganglionic fiber, it's releasing norepinephrine. And so that's the little pathway for that. It has a longer half-life, so acetylcholine is seconds, norepinephrine might be a couple of minutes. So there's a little bit, a very small amount of norepinephrine that will probably end up in circulation as a result of sympathetic nervous system activity. The great majority of it is a result of sympathetic nervous system activity causing the release of epinephrine from the adrenal gland. So remember, that was a big diffuse system of activity, of response for the sympathetic nervous system. So a little bit of it may diffuse away from the cleft and end up in the circulation, but not so much, because there is, is that right there? No, it must be on the next side. Okay, that's on that next slide. Okay, so it is produced, placed in vesicles, released into the synaptic cleft, and it's the fiber that's releasing noradrenaline is called an adrenergic fiber. The receptor is called an adrenergic receptor. So that's what I'm trying to say here. So it can diffuse away. How do you get rid of norepinephrine? You got rid of acetylcholine in two ways, really three ways. It can be bound by the receptor. It can be degraded by acetylcholinesterase, and it doesn't have a very naturally long half-life. And so with this, it can be bound by its adrenergic receptor. It can be catabolized. So there are a variety of chemicals that can catabolize norepinephrine. Monoamine oxidase is one of them. There are others, but it will cleave norepinephrine. And so you'll have a whole class of drugs called monoamine oxidase inhibitors. And so I don't know, you You've done psych, right? Okay, so those are coming up in psych. But anyway, that's why I want to mention that word here, because it relates to norepinephrine. But it's one of the things, like acetylcholinesterase is to acetylcholine. There are several things that can degrade norepinephrine. Monoamine oxidase is one of them, so MAO. But anyway, a lot of it gets just uptaken by the presynaptic cell, which is real handy. It doesn't even have to be degraded, it can just be reused in toto. So there's a thing called NET, or a norepinephrine transporter. And they're not located right in the synaptic cleft, which is cute, because you're taking something up that you're releasing right away wouldn't work. So it's really out there kind of peripherally to that axonal terminal, so that if anything diffuses away, it can just capture it and reutilize it by that. So that's pretty cute. A little bit is going to end up in the circulation, but again, really small amount. But just, because you do have a different half-life for those, you have built-in systems to deal with it, so that you're not continually enhancing or exciting that postsynaptic membrane. So adrenergic fibers are releasing norepinephrine. What are they? They're the postganglionic sympathetic nervous system fibers. Are the words pre and postganglionic now a blur right now? Okay. So that's just one of those things that those words can blur to you, I think, for some reason, and para and post and pre and all that. So do be very careful that when you read questions, and obviously this is true for any question that you ever read, but that you're a clear mind before you read the question, and you're actually reading the words that are there. I mean, that's very intuitive. I shouldn't even say that, but that's one of the things that you can bumble around in once you start to get a little. So anyway, I'm sure that's not you at all, so. But that's just be careful, have that image in your head, post and pre and all that. And then also adrenal medulla is releasing epinephrine, norepinephrine, but certainly more epinephrine. So I'm putting that there. So there's a lot of source for it, and you can get a very local verse, and also a whole systemic response to sympathetic stimulation. Adrenergic receptors, so those things that are sitting in membranes that can take up norepinephrine, are G-protein coupled receptors, so they do their thing. Cyclic AMP up, cyclic AMP down, or increase calcium and protein kinase C. And so, there are these subclasses. I'm the 11, the alpha and the beta. There's an alpha 1 and an alpha 2, a beta 1, a beta 2, and then a beta 3 on adipose tissue. So they all will follow this G protein thing. So the alpha 1s are using the IP3 DAG, that phosphatidylinositol pathway. Alpha 2s are decreasing cyclic AMP. So when I put AC there, I mean adenylate cyclase, because that makes cyclic AMP. If you're inhibiting it, you're decreasing cyclic AMP. There's a lot of letters. Beta 1s are activating or increasing cyclic AMP. Beta 2s, I didn't put what they do. They all do the same thing, I guess. Cyclic AMP. Yes, yeah, the betas are all doing increasing cyclic AMP. Although I'm not completely sure about adipose, but I believe that's true too. So really, it's only alpha 1 that's doing something different. So that's what they do, and that's where they sit. Here's another way of showing you what's really happening. So what is the point of the sympathetic nervous system, and that is to activate the body for threat or anxiety. And so goosebumps, dilated pupils, nice open bronchi for oxygen exchange, nice constricted vasculature for increased blood pressure, increased heart rate, increased heart contractility, increased ionotropy, increase, that's contractility, but increase the velocity or conduction rate of that odronotropy. So then, which receptor is sitting where to get that done? That's one of these charts. And this is where I'm going to ask specifically on you know, if you, norepinephrine received by a beta-2 receptor should cause which of the following? It's going to be on this exam. Because you've hit it, we just keep going over these things. But this is the point where, you know, that function with that receptor makes sense because it's sympathetic nervous system function. But I think you're probably hitting a lot of that along the way with pharmacology as well. So it just keeps coming because it's fun. That's one example there that shows you, oh yeah, all the betas are doing the increased cyclic AMP. That's one way of showing you. Here's another example. You know, I kind of tend to like these clean ones. That's just better for me, but that's the one I've put on there multiple times throughout various concentrations. So that should look a bit familiar. And then that one, which you can't read here, but I put it in your outline. So see that I did I?
Yeah.
Can you see your outline? And so I think there's 2 or 3 pages, and I can't remember where I lifted that. It was from one of the books, and it may have been, it was probably that Ganon text, and if not, it was that Junqueria text. But anyway, just so that you have like a thing in front of you also to look at, and not just a slide, because this is where you really just have to sit and get to know those receptors again or more or whatever. But I do think if you kind of know the distribution, you can figure out what's the thing that you already understand, know the one that's harder, and then you can always deduce the other. So like that function of the sympathetic nervous system is kind of easy to know, I think, or maybe easier to remember. And then you just have to know where are those sitting to get what response. And that's how the sympathetic nervous system is functioning. So there's really, I'm just going to leave that there and say, you know this. But it's not too crazy. It's not crazy. I swear, I'm not asking it crazy. I'm asking it like, what would you expect if a beta-2 adrenergic receptor is activated? And it'll be a list of 4 choices. One of them will be right. And you probably figured out one of them looks tempting. There's almost always a tempting choice and a right choice. So how do the 2 divisions, now just to function of the divisions, they're releasing their neurotransmitters and they're having some sort of effect on the other side of it. And how is that happening in terms of interaction? And one of them is antagonistic, which is really the word I've used all along. That if you have dual innervation, one system is on and one system is off. And so heart, respiratory, and GI systems, you certainly see that. So sympathetic is increasing heart rate, respiratory rate, and decreasing GI motility, which makes sense. So parasympathetic is decreasing heart rate, decreasing respiratory rate, and increasing digestive motility. So that you can get your stuff done, so that you can get your shit done. See what I did there? That's good stuff. And you'll see as you go into practice just how important that is to people. Now, the other things that the divisions just have under their control, sympathetic tone. And so this is just this sort of, especially vasoconstriction, is this little compression of the arterioles on their content to create a constant blood pressure that's appropriate. That's how we know when you take that reading, that's really the sympathetic tone that's creating that blood pressure reading. And so you have like a set tone and then you can increase it very quickly. Parasympathetic tone is really dominating the heart and the digestive tract. So they have a little bit of specialty even though there is dual interaction. Cooperative effects, pupils. Isn't that interesting that the well, when you think about it and you see a slide like that, that your pupils and your external genitalia are the other kind of like the outliers of the autonomic nervous system, that explains a lot. I'm just going to drop that right there. Control of pupil diameter, so sympathetic is widening as the mydriasis, I don't know, I can't say that, widens. But you see that on boards, that word is on board exams, so just for some reason. And then the constriction is meiosis, and that was something that's easier to say, so for some reason. But those are two words that you think, I don't need to know those, nobody uses those words, board exams do. So anyway, just know that. And then external genitalia, you know, one gets you there and one gets let's move on. One division innervation is seen where the sympathetic nervous system is single innervation. There isn't dual innervation, but single innervation. It's important to know these. Adrenal medulla, that's one. Adrenal medulla is going to create a circulating adrenaline or epinephrine. Erector pili muscle, so goosebumps, which is so unique. But if you looked at, this is where I've thought of it, is if you look at a horse, next time you're looking at a horse, have you noticed our cows, you notice their skin is reacting to like flies landing on them and stuff, and you just get, so I think, well, that's what our like erector pili response is really doing. We just don't have that much hair. I mean, I do, but a lot of you, you know what I mean, you just don't have that much hair so that you would see entire waves of should I move on? Should I wax? But you know, so that's kind of, I don't know what importance it really has for us. I mean, we are aware of that sensation and that alertness, but probably it's something that's a vestigial. If you had more fur, it would be it would make more sense to have all that control over every single hair. So that's amazing. But it certainly goes into our ability to sense light touch as well, I think. Sweat glands are part of that. Kidneys are under single innervation, and so the juxtaglomerular apparatus releases renin as a result of sympathetic nervous innervation, or one of the reasons renin is released. Direct innervation by the sympathetic nervous system. And it is another level. You can have local vasoconstriction, or you can have the systemic sort of vasoconstriction to have this other bigger, longer lasting way of affecting blood pressure. So most blood vessels are under a single innervation with the sympathetic nervous system. Thermoregulation is one. The blood can be shunted toward the skin or away from the skin. If you're hot, you can put blood toward the skin to create some sort of evaporative sort of action along with sweat gland activity. So thermal regulation from an exterior sort of standpoint, or you can shunt blood inward to keep the core warm, and you're willing to lose extremities to keep the core warm if you're in a hypothermia situation. And so this is why frostbite works, is because the sympathetic nervous system is keeping blood so that you can keep it to the core and get it to the brain, because it's more important than your feet under threatening conditions. So that's a unique role of the sympathetic nervous system. Metabolic effects, the parasympathetic system is running the digestive system. The sympathetic system will help the endocrine system with blood sugar regulation, in a sense, by not regulation so much as readiness, by having plenty of fuel available in the blood. So that would be glucose, that would also be fats. So it's a diffuse effect by circulating epinephrine from the adrenal gland, or any norepinephrine. Increase the metabolic rate. I put MR for metabolic rate there. Did I tell you that they took the letters MR off of all? Did I say this? I feel like I had it. Off of all federal for mental retardation as an effort. And so no forms, federal forms use the terminology or diagnosis of mental retardation. So I just thought of that, because we're trying to get away from use of that word. Anyways, this means metabolic rate here, increasing blood sugar, mobilizing fat, what we really do. So that's a sympathetic thing, really adrenal, but the adrenal gland is releasing its stuff because of direct stimulation from the sympathetic nervous system. So they act in concert together. And then increased mental alertness through this. That's not renin-angiotensin system, but it's reticular activating system. So that reticular system that is sending information all over the place, not just nuclei, but where all of that activation of the cortex, reticular activating system for alertness. And that makes sense. That should be under sympathetic rule, so that you're aware of your surroundings, and then you have all of everything else is readiness for you to run from that lion in the Serengeti after you climbed out of that tree. Was that the? Yeah. That could have been me. That's sad. How do you control all this? Well, you know how pretty much know how you're exiting and where you're going, but what's the higher center control? Hypothalamus, main integration center of the ANS. So, do you remember some of those respiratory centers and those pesky respiratory and cardiac centers? Well, that's part of this whole autonomic control, and so this is how we were feeding information to kind of help run the heart rate. So, and it's not just a matter of setting the heart rate low or setting the heart rate high. We are able to balance and integrate that excitation or inhibition via higher centers, the hypothalamus. So the hypothalamus is really the thing that's understanding what's going on in the whole body and then sending information to these various centers to control their thing. So the hypothalamus is controlling cardiac and blood pressure, body temperature, water balance, emotional things, rage, pleasure, biological drives, thirst, hunger, sex. I was going to say I should put sex up there. Oh, I did. So, you know, it's an integration for all of these things, and then the autonomic nervous system can dilate your pupils, make you want to eat or reproduce. Brainstem and spinal cord. Reticular formation of brainstem appears to have the most influence over ANS function. There are two arms of the reticular system. Reticular activating system, or RAS, projects widely to the hypothalamus. So information, sensory information coming to the brainstem is then being relayed all over the brain so that your sensory information makes sense. So how is any of this even, why is any of this happening? Why is any of the ANS stuff happening? It's because there's some sensation about the external environment or the internal environment. Like, what's the blood pressure sitting here in this carotid body? Or what's, all that stuff. What was that sensation, or what was that thing? Not just reflexes, but all this information has to ascend for integration and then responses via somatic or autonomic divisions. So projecting widely, maintaining arousal state and readiness. The other arm is the motor arm. So you're arousing the sensory system is informing the brain, and then the brain is sending information out via motor. So motor to autonomic motor centers or to skeletal centers, because you have a lot of involuntary skeletal control as well. There are a lot of reflex arcs, defecation, micturition, and oculomotor movement and stuff like that, which is reflexive. The information then again does ascend to the brain for understanding of what's going on. Finally, there is this enteric nervous system, and we'll talk about it in the digestive system, but it really is a branch of the autonomic nervous system, because it's there are these self-regulating involuntary things. So functions a lot like the autonomic nervous system, but it is specific and contained within the gut, to run the gut. So the parasympathetic system is running the gut, but the gut has its own system that is sensing what's going on within itself and has its own little reflex arc to control motility and so forth on the the other side, so that there's a little bit of a dual thing. So anyway, that's called the enteric nervous system. It's in the wall of the digestive tract itself with sensory information and motor information. So afferents, interneurons, looks just like a reflex arc. Sensory in, process via an interneuron, and then motor out. But it falls outside of what we're talking about with autonomic nervous system, but it really is considered a third branch of that. Autonomic nervous system nerves connect the enteric nervous system to the CNS to allow for coordination. So it's there, and just to kind of show you what that's supposed to look like, the alimentary canal is just, you're a donut, The GI tract is just the middle, and so all along that you have these two layers of enteric nervous system sandwiched between layers of the digestive tube. And so anyway, I'm putting that there. I'm not asking questions about that. Maybe the words enteric nervous system might appear on some question, but not about that question. I don't think I did. But I just want to say it here because it's sort of technically often covered within autonomic nervous system, but we'll talk more about it during digestive. And I think that's it. Yes. So anyway, what I hope you got then today was an outline and were the slides then. So that sort of ended up not being within the D2L system, but I will make sure that it gets there because I think it should be there, so I'll ensure that happens. I don't think we're going to lecture, true? Okay, so I know you have a lot to enjoy from today, so please enjoy that. And then I'm not back until